Hello everyone, my name is Farzane Abdoli and I'm going to present the paper Deep Deterministic Policy Gradient in Acoustic to Articulatory Inversion. My supervisors in this work are Dr. Sheikhzade and Dr. Pourahmadi. In this presentation, we'll go through introduction, problem definition, proposed method, results, conclusion, and references. Before defining acoustic to articulatory inversion, I want to talk about the human voice generation process. Vocal tract articulators like lips, tongue, velum, and jaw play the main role in the speech generation process. Human can produce acoustic signal by moving these vocal tract articulators, and in this way, an audible sound is transformed from vocal fold into speech. Acoustic to articulatory inversion or AA inversion extracts the articulatory trajectories or parameters from a given acoustic signal. In other words, it inverts the human speech production. But the question is, what is this inversion useful for? Researchers' interest for this topic can be divided into two groups: applicative interest, like automatic speech recognition, computer-aided language learning, speech synthesis, and low bitrate speech coding, and theoretical interest, like a better knowledge of speech production and the better comprehension of audio-visual integration. How can a vocal tract be modeled? Numerous models have been proposed till now. We use the three-dimensional vocal tract model developed by Peter Birchholz, which consists of 23 articulatory and 6 glottis parameters. This figure shows the model and the definition of these vocal tract articulators in 2 dimensions, and this table shows the range of these parameters for a German male speaker. As an application of this 3-dimensional model, we can refer to Vocal Tract Lab software or VTL software. VTL is an articulatory speech synthesizer and a tool to visualize and explore the mechanisms of speech production with regard to articulation, acoustic, and control. We use this speech synthesizer in our work, and I will explain more about it in upcoming slides. Now, let's talk about the acoustic to articulatory inversion approaches, and then I will explain about my method. Different approaches have been proposed for AA inversion problem that can be separated in two groups. And the first one is data-driven methods like hidden Markovian models, Gaussian mixture models, Kalman filters, and neural networks. This approach tries to find an estimator for the nonlinear relation between acoustic signal and the articulatory gestures. The second methods are analysis by synthesis methods, and an example of this method is codebook method. As it is shown in this figure, in codebook method, after feature extraction from the acoustic signal, a search algorithm finds the best available matching value for articulatory parameters in the codebook. And then, after finding a suitable vocal tract parameters, articulatory synthesizer produces an acoustic signal according to the input vocal tract parameters. Finally, an optimization algorithm minimizes the distance measured between the natural acoustic features and synthesized acoustic features. Although these methods have shown the ability to achieve the desired vocal tract parameters, they need huge parallel acoustic articulatory dataset. And their functionality depends on the quality of dataset or the codebook. How can we obtain parallel acoustic articulatory dataset? Is it a difficult task or an easy one? Two methods for this purpose are available. The first one is static methods like MRI or X-ray scan. In this method, a person or a speaker produces acoustic signal while imaging is in progress. The second method is dynamic method like EMA, OPG, and EPG. Both of these methods have some advantages and disadvantages like ability to model movement, need long time of pronouncing, expenses, and noise. And there are also concerns about radiation to subject set, cumbersomeness, expenses, and again noise. So, obtaining parallel acoustic articulatory dataset is really challenging and it is not an easy task. Now it's time to define the main problem. As I explained, in some approaches like data-driven methods in training phase, parallel acoustic articulatory data is necessary to estimate the nonlinear relation between acoustic signal and articulatory features. In codebook methods, also having a large codebook with good coverage is needed. It's a good idea to define a new approach which does not need MRI or EMA methods for obtaining huge parallel acoustic articulatory data sets and can straightly estimate the parameters by itself. The proposed method is a type of analysis by synthesis method, and fortunately, no need to huge paired dataset. This approach evaluates the fitness of the estimated articulatory parameters by synthesizing speech signals using the synthesizer and measuring the similarity between the target and the synthesized speech. Given a target, in other words, given a target speech sound and the physical speech synthesis model, a sequence of optimal articulatory parameter that produces the highest fitness is searched, but not in a codebook. The search algorithm here is a DDPG method that is responsible for estimation of articulatory parameters with regard to distance measure. The articulatory synthesizer is a VTL. The distance measure is cepstral distance. Deep deterministic policy gradient, or DDPG, is a kind of reinforcement learning algorithm. Reinforcement learning is the training of machine learning models to make a sequence of decisions while interacting with an environment. As it is described in this figure, an agent learns to achieve a goal in an uncertain, potentially complex environment. The computer employs trial and error to come up with a solution to the problem. Interactive learning properties suggest a possible reinforcement learning approach, the analysis by synthesis method in acoustic to articulatory inversion. Although deep RL algorithms have been applied to many complex tasks and made breakthroughs in them, few studies have checked the application of the proposed algorithm in the scope of the acoustic to articulatory inversion problem. Here, we are exploring the functionality of DDPG in solving acoustic to articulatory inversion problem and some of its challenges. To formulate the AA inversion problem based on RL approach, I'm going to define the main concepts of reinforcement learning in my problem. Here, the DPG algorithm is the agent of the method, which decides about actions. DDPG is an actor-critic algorithm that is model-free and off-policy. This method can find optimal policies in continuous action spaces with the help of deep function approximators. A status space is a 19-dimensional mid-frequency cepstral coefficients, or MFCC, of a speech. The other concept is action space. Articulatory parameter values are our action space. For synthesizing a speech with the vocal tract lab, 14 articulatory parameters needed to be adjusted for a special speaker. As researchers stated, some of these 14 values may be dependent on others. Changing one articulatory parameters will be effective in another parameter's value. Because of these complex nonlinear mapping between a few cepstral coefficients as input and continuous dependent parameters, simultaneous estimation of all of these parameters is a really challenging task. So, to solve this problem, an iterative DDPG optimization algorithm is proposed here. First, initial values for all parameters are adjusted, and I will explain about the initial value later. In first iteration, DDPG tries to find the best value for hx, while the other values are fixed at their initial value. In the second step, hx is fixed at its best learned value, hy is being learned, and the other parameters are fixed at their initial value. This process will be repeated for all 14 parameters. And again it will start from the beginning, and again it will learn all the parameters value until a good convergence in reward function will be observed. For initial value, we can use random values or other speakers parameter. Environment is as I described before, environment is a vocal track lab. The reward function is negative short-term capsular distance between the synthesized speech and the original one, as it is described here. CO and CS are capsular matrices of original speech and synthesized one. M is the number of frames, and N is the capstrom length of each frame. To evaluate the results, we use two matrices, the quality of synthesized sound and the feedback reward. Both of these metrics are compatible with each other. Here are two figures. The left one is a reward function for A sound. We can see a reward improvement in the process of learning the parameters. And the right figure is vocal tract shape produced from approximated parameters. These tables report the results of prediction and true values for parameters for A, E, O, and I sound. These tables also indicate that learning important parameters is roughly accurate. There are also some items that are not predicted very close to the real values, and this can be illustrated as their low influence on the quality of related synthesized sound. And it's time to conclude the presentation. In this presentation, we talked about acoustic articulatory inversion, its methods, and existing challenges. We explored the possibility of using reinforcement learning algorithm, DDPG, in solving the acoustic articulatory inversion problem. And the results were really encouraging, and there are a lot to do in future in this scope. These are the main references, and finally, thanks for your attention.